Welcome to a video on trigonometric equations. So in this video we are going to solve equations for unique solutions if they exist. Now we've seen a trigonometric equation before. It's just an equation that contains a trig expression and also a variable. Okay, some are identities, and we got to remember things like sine squared x plus cosine squared x equals 1 is an identity, which means it's always true for any x that you want to put in there. That's always going to be true. All right, but what we want is equations that are just sometimes true. They're not true for every x, they're just sometimes true. Like example, the sine of x equals a half. Sine is not always, the sine of an input is not always a half. It can be any number between -1 and +1. So this isn't always true, but we do know that it is true sometimes because, for example, the sine of pi over 6 is a half. So pi over 6 is a solution to this. Anything that you can plug in for the variable and make a true statement is a solution. So pi over 6 does make a solution. But as we've seen, because the sine, cosine, and the all 6 trig functions are periodic, if there is one solution, then we can just keep going around the circle over and over and over again and just keep picking up more and more and more solutions. So remember, the sine curve, we get a wave. So if we take that wave, the sine wave, and we just graph that, the left-hand side, and then we also graph the right side, y equals a half, we get a graph that intersects as many times as we want it to. So all of these are solutions to this, anything that makes it true. This is the sine function, and the sine is equal to 1/2 when x is pi over 6. And then again, when it's 5 pi over 6, on our way back down in the unit circle, we also hit a half. If you think about the unit circle, sine is equal to, the sine's the y-coordinate, so it's equal to a half at pi over 6 when we're rotating up, and then it gets up to 1 and it starts coming back down. And because it's going to come back down to 0 again here at 180, it has to pass by 1/2 again, and it does right here at 5 pi over 6. All right, and then it doesn't hit it again as we dip down in the negatives, but then when we come back up and we've gone all the way around one time, 2 pi, all right, 2 pi is 12 pi over 6, and then one more pi over 6 would be 13 pi over 6. So we're just going to keep hitting that. So we're going to get pi over 6 and 5 pi over 6 plus 2 pi, and then plus 2 pi, plus 4 pi, plus 4 pi. So we're going to hit these two things over and over again every time we rotate around 2 pi. And that's what these solutions are. It's just pi over 6 and 5 pi over 6, and then we add a period, and we hit it again, and we add a period because we just keep going around the circle, hitting those 2 points on the circle over and over and over and over again. Now that's how trig functions, trig equations work. Okay, we're coming up with all these different things, but we don't want to write that as our solution. We don't want to write pi over 6, 5 pi over 6, 13, and then like do something like dot dot dot, like the pattern continues, because there's not really a pattern here. I mean, technically there is, but the way we write it is that x could have been pi over 6, all right, and then that part is that we're on our way up, and then when we come back down, it's completely, the gap between here and the gap between here is different. So that's why I was saying the dot 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 doesn't really work, because there is a pattern. It's, we're adding 4 pi over 6 or 2 pi over 3, and then we're adding 8 pi over 6 or 4 pi over 3. The gap between it does have a pattern. 2 pi over 3, 4 pi over 3, 2 pi over 3, 4 pi over 3. But we still wouldn't even want to write that. What we do is we basically focus on one at a time in this pattern, so in one period, and then we add 2 pi some integer number of times. So n is some integer. And then there's another solution that occurs at 5 pi over 6 plus, again, whatever the period is, times n. And then n is just some integer. So by an integer means positive and negative whole numbers. And that allows us to go this way and this way. So we start here and we subtract 2 pi. Or we start here and we add 2 pi, okay? And we just keep that going over and over and over again. So 2 pi times n, this is the period, all right, the period between these similar solutions. And then n is just that we just could go around as many times as we want to in either direction. All right, but let's go through. Ultimately we're going to get a trigonometric function isolated equal to a number, but we don't have to graph it every time. Okay, we can think through the solutions. It will help to have your unit circle out, but we don't have to graph the trig function in the right-hand side every time. So let's do this and see if we can think through it and have the unit circle help us out. So what you want to do is you want to get, they're both sines, we want to get all the sines collected on one side and then the non-trig functions on the other. So I'm going to move all the sines to one side and the numbers to the other. So notice this is bigger than this, so just to avoid negatives, I'm going to move the sines to the right, and then I'm going to move the numbers to the left. So I'm going to add 1, and that way I don't have any numbers on the right. So I add 1 to this side. That gives me a -1, and then I'm going to divide both sides by 2 to isolate sine. So that's what I was talking about before, that we want to get the trig functions isolated on one side and a number on the other side. So now we got the sine is equal to +1/2. So I'm going to bring in my unit circle. So we want to know, where is sine equal to -1/2? Okay, so there's it is, +1/2. All right, +1/2. Sine's the y-coordinate, so it's not going to be up here in quadrants 1 or 2. It's going to have to be down here. So there's sine equal to -1/2. Remember, it's the y-coordinate, and there it is too. So we got 7π/6 and 11π/6. So our general solution is going to be, oops, let me get my pen back, x equals 7π/6 plus 2π times n, and 11π/6 plus 2π times n. Again, these are the things I see on the unit circle, and this is just flipping me around the unit circle as many times as we want to. Okay, this is called the general solution, if we're not told to find specific ones. And what they will do for a specific one is they'll say x has to be between 0 and 2π, the first positive revolution around the unit circle. So here's one that has that restriction on x, so we're not allowed to just keep going around the unit circle, so we don't need the general solution for this one. Okay, now I want the trig function isolated on one side and a number on the other, so I've got that. Now the thing here is tangent, there's a 3x, it's not just x. So where's tangent equal to 1? If you remember, tangent's the slope, and tangent's equal to 1 on the unit circle when y is equal to x, or the x coordinate is equal to the y coordinate. So that's going to be at 45 degrees, or π/4 radians. The x and y coordinates are the same. So at π/4, we are at the right place. And then along that same line, this is 1π/4, 2π/4, 3π/4, 4π/4, 5π/4. At 5π/4, we're on that same line, y equals x. And so that's another place where we're equal all the way through. Okay, so the tangent of π/4 is equal to 1. All right. So what does that mean? That means that 3x is equal to π/4. All right. So 3x is equal to π/4. So that means that x is equal to π/12. All right. Now, how do I get from π/4 to 5π/4? Remember, this is a straight line. So just the period of tangent is pi. So I would add pi to this, and I would keep getting more solutions. So pi times n, because again, if I add pi, I'm right to here. If I add another pi, I'm back to here. If I subtract pi, I'm here. So this is the general solution. All right, π/4 plus π/n, if this were just x. But it's not just x, it's 3x. So when we divide by 3, the π/4 became π/12. 4 times the 3 that we're dividing by is 12. But this would also become π/3 times n. So these are the general solutions. Now I don't need general solutions, I just need something between 0 and 2π. So what does that mean? Well, that means I'm going to take this pi over 12 and I'm going to add pi over 3 over and over again until I go beyond 2 pi, and that'll give me all my solutions. Alright, so pi over 12 plus pi over 3, that's the same thing as pi over 12 plus 4 pi over 12. Alright, just getting a common denominator. Pi over 3 and 4 pi over 12 are the same. That's 5 pi over 12. Okay, that's between 0 and 2 pi. Alright, 24 pi over 12 is the next number that's not going to be. So that's also a solution. Alright, so pi over 12 is our first solution. That's a solution. 5 pi over 12 is the next one. Now, you're going to see the pattern as soon as I do it the next time. So 5 pi over 12 is a solution. I keep adding pi over 3 to get my next solution. Well, pi over 3 is always going to be 4 pi over 12, which is now going to be 9 pi over 12. Alright, 9 pi over 12 will reduce though. That's 3 pi over 4. That's the solution. Alright, so 1 pi over 12, 5 pi over 12. I just keep adding 4. So 9 pi over 12 plus another 4 pi over 12 will be 13 pi over 12. Alright, that's the solution. Add another 4 pi over 12. I'll have 17 pi over 12. That's the solution. Alright, again, all I'm doing is adding pi over 3, and that's just the pi. But because it's 3x, and that's the period for this particular function is pi over 3. So I'm adding pi over 3 over and over, which is the same thing as 4 pi over 12. 4 pi over 12 again will get me to 21 pi over 12, which once again will reduce because of the common 3 as 7 pi over 4. That's another solution. Now the next one, if I added another 4 pi over 12, I would get 25 pi over 12. Alright, 24 pi over 12 is 2 pi. So 25 pi over 12 would be too big. So this is the last one. So there's our solution. There's 1, 2, 3, 4, 5, 6, 7 solutions within that first revolution. Okay, and that's what all you would list. Okay, so I always tell people, even though it doesn't want the general solution, still get the general solution. Here's the general solution, and then use that to come up with a way to find all the possible solutions that live in this region. Alright, now let's graph it with Desmos. Alright, so I got in y equals tangent 3x. That's the left-hand side of the original. Y equals 1 is the right-hand side of the original, and we can see all those places where they intersect. Now, what I want to do is I want to make our thing move up at pi over 12 intervals. So I'm going to change this to go from the x-axis to go from 0 to 2 pi. So I just write into pi for pi. And then I want the step to be pi over 12. Alright, and the y-axis we don't need to go down that low. Let's just go from 0 and let's go to 1.5, just so we can go up high enough to see the solutions. Alright, so let me close that off and blow it up so we can see. So I got to move in a little bit so you can actually see the bottom of this. So there's the pi over 6, pi over 3. This is pi over 12, 1, where they hit. This is 5 pi over 12, 1, 3 pi over 4, 13 pi over 12, 17 pi over 12, and then there's that 7 pi over 4, which was our next to last. Nope, that was our last one. Okay, so there is the way you can use Desmos to help you with this. Again, what did I do? I move that over. I put them both in, and then I changed the axes with this graph settings tool to go from the region it said 0 to 2 pi, and then I used the size between there, which is basically that first one that I got, the pi over 12, as my step size, so I could get those solutions. That whatever that denominator is that shows up that won't reduce, that's what you want to make your step size. So there's 5 pi over 12, 13 pi over 12. So 12 was that biggest denominator that showed up. So I made the step size pi over 12, and that should make it to where it works.